So let me start by wishing you all a very happy Pi Day. Today is 3.14, so happy Pi Day. I actually know where there are Pi Day songs to be found, but I have agreed not to embarrass Lynn by making her stand up and sing them with me. So the exams have gone to the exam service, and the results and analysis have come back to me. And I'm going to show you in advance the summary. This may be hard to, I guess that's easy enough to read. The exam service, as I said the other time, provides us, whoops, did I start the recording? Okay. As I said for the first exam, the exam service provides us two kinds of numbers. There's a difficulty for how many people get it right or wrong, and then there's a reliability, which is a way of judging whether it's a good or a bad question. That is, if students know the other stuff on the test, get that question right as well, that's one measure for its quality as a question. If it's random who gets it right, it's probably not a good question. If the more stuff you know on the test, the worse you do on that question, it's a terrible question. So these numbers give me kind of a handle on, was the question ambiguous, was it misguided, and so on. Based on the analysis of those numbers, I can't identify any questions on the test that were bad questions, ones where they were inherently impossible to answer correctly, or that they led people who know the subject well to give the wrong answer or anything like that. However, a number of them were more difficult than I had intended the test to be. I'm not quite sure why yet. I'm going to be analyzing the wrong answers some more to see if there's a pattern to it, and if there is, I will try to correct the misapprehensions all at once. I can't give you a good summary of them right now. But since there were a number of these questions that were more difficult than they were intended to be, the way I'm going to deal with this year is a little different than in the past. I don't know if you have friends you talk to about this. But what I'm going to do is add 15 points to all people's scores rather than lowering the grade cut thresholds. I try to be fair. I really do. This will give a few students who will actually get more than 100 points, surprisingly few, which is one of the reasons why I think the test was too hard. And those lucky souls will get to keep those extra points as bonus points as a measure of having, in fact, gotten difficult questions right. Apart from that, though, there's a second concern from my perspective. This point adjustment is my best guess at trying to correct what I think may have been more difficult than they were meant to be. However, the pattern of errors is concerning me because it's bimodal. That is, a good chunk of the class came in one cluster, and then there's a second clear cluster about 20 points lower than that. And so there's a population of students here who has a substantially weaker grasp of this material than the average student in the class. And I'm going to try to send emails to that group of students to say, please come talk to us, help us kind of see if we can diagnose where the difficulties are, offer you study strategies, and so on. But students who are in that group, if they continue to perform at this level, are going to not be doing well in the course overall. So if you find that your test score is below 70 after this adjustment, you may well want to get in touch with me or with Lynn and work out new study strategies. Are there any questions about specific questions on the test that weren't fairly obvious from the posted answers? There were a few sort of English questions. Most means definitely more than half. So you can't have most being alpha helix and most being beta sheet. That's mathematically impossible. But apart from that, are there other issues that people want to bring up? Okay, let's go on to happier topics like oxidative phosphorylation. Oh, sorry. Question? Quiet, please, so I can hear his question. We're going to hand those around, but it isn't exactly extra credit. We're going to do that about the middle of the class. We keep a record of who's filed those cards, and if someone's on the borderline at the end, that tips the difference. This is different from extra credit because it's not added on up front. It's used to decide the ties. Okay? But we're going to do that in a little bit to make sure anybody who actually gets here a little bit late still gets a chance at it. So, okay. We talked on Monday Friday and Monday about the citric acid cycle. The citric acid cycle, if we could calm down. There we go. We noticed in the citric acid cycle we could oxidize carbons and in the process generate fantabulous amounts of NADH, the reduced form of NAD that serves as an electron carrier. NADH by itself is not a widely useful compound. It's not used biosynthetically. That's what NADPH is used for. In order to get energy out of it, we have to somehow or other get those electrons out of it and manipulate them some other way. And that's what oxidative phosphorylation is for. Let's see if we can get my pointer back. So here is the citric acid cycle, and it's producing vast quantities of NADH and substantial quantities of QH2, the reduced forms there. And what oxidative phosphorylation is going to do is provide a way to use these electrons to generate a proton gradient, a difference in proton concentration. And we're going to see how a proton gradient can in turn be used to make ATP. And the advantage of all this is it allows us to use one common carrier or a couple of common carriers for electrons and produce a common energy vehicle or energy compound, ATP. So a very, very great array of fuels has a common output of NADH, which in turn has the common output of ATP. So the principal carriers that are going to feed electrons into oxidative phosphorylation, we're going to see that the oxidative part is because it involves oxygen. We've seen substrate level phosphorylation already. This is oxidative phosphorylation that involves oxygen. The principal electron carriers here are NADH and FADH2. Glycolysis is one source. A lot of it's coming through the citric acid cycle. A lot of it's going to come from fatty acid oxidation. We're going to see in a little bit that fatty acid oxidation is also an abundant supply of these reduced compounds. These are energy rich, but not because they have a high energy bond that you can point to the way you can in ATP. They're energy rich because they have electrons in them that have a high transfer potential. And we're going to see in a slide or two what a high transfer potential actually means. But their energy richness lies in the state of their electrons. Oxidative phosphorylation gets its name because we're forming ATP. We're doing that by taking the electrons that are carried by these two electron carriers, transferring it to O2, and in the process making water. So oxygen is an essential part of this, which makes it oxidative phosphorylation. We're going to see that it's a very localized process. So here is a mitochondrion. This is a transmission electron micrograph. Here we can sort of see that the mitochondrion has a double membrane there. A little hard to see that it's double. You can see it there, I think. And it has these inner membrane extensions of that membrane. And the electron movement is going to be in the plane of that membrane for the most part. But electron transport is going to be used to drive proton movement to create a proton gradient. That proton gradient then has chemical potential in it. And it's like a water behind a dam. The mitochondrion is going to let the electrons flow back and drive ATP synthesis the way water coming out of a mill race can drive the milling of flour. So here we have sort of a classical mitochondrion. This is the sort of standard oval shape that's frequently seen. I'll just mention as a note of realism that mitochondria come in a wide variety of shapes, but certainly some of them are oval. And the mitochondrion is a really metabolism-rich little organelle for the cell. And we're going to see within it different pathways localized to different parts of the mitochondrion. Just to give you some anatomical terms, if you like, for the parts of the mitochondrion to start off with, there's an outer membrane, which is the outer membrane. There's an inner membrane, which is the inner membrane. There's a space between those two membranes, all right, between the outer and the inner membrane. It's called the intermembrane space. And in places where the inner membrane has folded out like this, there's little extensions of it folding out. Those are called cristae, or singular of a crista. The extensions of the inner membrane are called crista, but they are still continuous with the inner membrane. And then in the very innermost part of it, in the very center, completely surrounded by the inner membrane, is more material called the matrix. So the matrix is the stuff that's right in the inside of it. Now, the different pathways that we're going to look at happen in different parts of the mitochondrion. We've already looked at the citric acid cycle, for instance. We didn't emphasize the fact that the citric acid cycle only occurs here in the matrix of the mitochondrion, with the exception of that one enzyme that's an integral membrane protein, right? Succinyl dehydrogenase. We are also going to see that fatty acid oxidation is localized to the mitochondrion in the matrix. However, the electron transport we're going to look at for oxidative phosphorylation is embedded in the inner mitochondrial membrane. So that's the surface that's going to contain all those electrons, and they're never going to be free. They're going to be passed from protein to protein like a bucket brigade. This is another way to make a diagram of that, if you like. So this here should be thought of as the inner mitochondrial membrane. The electron transfers that happen in the course of oxidative phosphorylation are associated with these integral membrane proteins that generate a proton gradient. They move protons one way or another to the intermembrane space out of the matrix. And then as in the process, they're generating H2O. Those electrons get transferred to the oxygen. The protons that accumulate in that intermembrane space can flow back through the ATP synthase and in the process make ATP. A very strange process. We'll see how strange. To get a grip on what's going on in the electron transport chain for oxidative phosphorylation, we might benefit from taking a little look at redox reactions again and some of the math behind them and how we talk about them. Redox reaction is just short for oxidation reduction reaction, because in any case when there's one, there's the other. Redox reactions always involve the transfer of electrons from one compound to another. What makes it sometimes a little difficult to remember which is that reduction is gaining electrons. If you have more electrons, which are E minus, it will reduce your valence state. And here we can see an example that should be familiar to us from hemoglobin. Fe plus 3 plus 1 electron with its negative charge becomes Fe plus 2. So the iron has been reduced. Its valence number is smaller now. It's gained electrons. A reducing agent, or a reductant, can add electrons to something else. And when a reducing agent does that, it becomes oxidized. And the converse is also true. An oxidizing agent or an oxidant can take electrons away from a molecule, and in the process, it will be reduced. And I think one of the problems with redox reactions is these words get used back and forth for the two halves of the equation. They start to sound a little bit empty. So let's take a little concrete example. Here is one we've seen before. We saw this in glycolysis. Pyruvate plus NADH can go backwards and forwards. It's a lactate and NAD+, right? Well, NADH is the reduced form. NAD+ is the oxidized form of these compounds. So in this reaction, NADH can reduce pyruvate and in the process become oxidized. Or if you want to think of it the other way, lactate can reduce NAD+, and in the process, it becomes oxidized to pyruvate. But there's always one member of the pair that's oxidized and one pair that's reduced. Okay. This is showing you that reaction at the molecular level to remind you of what it looks like on carbon atoms. So here's pyruvate 2 bonds to a carbon, 2 bonds to an oxygen, so it's a relatively oxidized carbon. At the end of the reaction, it's got 1 bond to an oxygen and 1 to a hydrogen, so it is now reduced relative to pyruvate. Here's NADH. It's got its 2 hydrogens flapping up there in the breeze like a pennant, and after it reduces the pyruvate, it has only the 1 hydrogen left up there. So you can see it at the structural level. When you have a covalent bond, the more electron-negative atom in the pair, in that bond, is the one that is assigned the electron. And so a hydrogen is deemed to give its electron to carbon. So here's in this one, the carbon gets the share of that electron, whereas carbon would give its electrons to oxygen. So you've got 2 bonds to the oxygen. It's giving up electrons. These are a couple more examples of oxidation and reduction. So this is a relatively reduced form of vitamin C and a relatively oxidized form of vitamin C. Vitamin C is very important in redox reactions, some redox reactions. This is showing the reaction between hydrogen and fluorine gases to make hydrogen fluoride, and in the process, the fluorine's getting reduced to fluoride. Any compound has a tendency to give up or to pick up electrons. Just as enzymatic reactions have a tendency to go in one direction or the other, compounds can tend to give up or pick up electrons. And there's a way to measure this using the reduction potential, E prime sub 0. And it's a little more complicated to think about than looking at the delta G for a reaction because you're comparing pairs. There's always a redox couple of someone who's oxidized and someone who's reduced. And so to measure that, there are 2 cells, one that's going to have your compound X and its reduced companion at 1 molar, and it's going to be compared against protons and hydrogen gas, so that the protons and hydrogen gas become the reference point for the other things. So in this example, for an overall reaction, the X minus, the reduced form, plus a proton can go to X plus a half a hydrogen gas. And if we break that down into what are called the half reactions, so we can sort of piece apart where the electrons are, X minus can go to X plus an electron, and H plus plus an electron goes to half of a hydrogen gas. This is simply to sort of see where the electron balance is because there are not free electrons in biological systems. The takeaway for this is that the larger the E0 for something, the more likely it is that it will accept electrons at pH 7. So it's a way of comparing the tendency of a compound to gain or reduce other compounds. And the range across those values can be very great. So here at the bottom, we're looking at oxygen with protons as the redox, and water as its redox pair here. And you can see it has a redox potential of 0.82. And this is a sign that the oxidant in this couple is very, very likely to pick up electrons. When you have a very negative E0, it's a sign that the reductant in that is very, very likely to give electrons. And so it allows us to compare and rank order different compounds and their tendency to reduce or to oxidize other compounds. I don't expect you to memorize these in detail. You may find it interesting to look at where in this scale the different compounds are because we're going to see most of these compounds in the pathways in the next couple of chapters. But so when we're looking at redox reactions, we can break them apart in thinking about them into their half reactions. So the one we started off talking about pyruvate and NADH, and actually a proton to keep strict books, going to lactate and NAD+, can be thought of as pyruvate and protons and electrons making lactate, and separately NAD plus protons, electrons, making NADH. So we can see which one is actually getting electrons or losing electrons in those half reactions. Here we're looking at the tendency of electrons to move, or the, rather properly speaking, I think what I would say here is that part of the takeaway here is that electrons can move better through proteins than they can through vacuum. That is, the overall structure of the protein is more conducive to that than just empty nothingness. However, there is a limit to how far you can go. So if you talk about pushing a greater voltage difference across it, you can have more electrons moving up to a point, and then with a great enough difference, you actually get fewer electrons moving. It's something like the way we jam up at the door when there's too many people coming at once. So there's such a thing as too much of a good thing. Let's take a look at the respiratory chain that's at the heart, if you like, of oxidative phosphorylation. What we're going to see is that there are 3 proton pumps involved with it, and a complex that is integrally connected to the citric acid cycle. In addition to the 3 complexes, so we've got these sort of rounded boxes are all proton pumps that are integral membrane complexes. In addition to those complexes, those electrons have to get between the complexes, and there are carriers for that. The carriers in particular are Q, which is short for ubiquinone, and cytochrome C. So you can see here NADH, the soluble electron carrier, feeding into the top of the respiratory chain, Q carrying at the second step, cytochrome C between the second and third components of it. And then the final electron acceptor is going to be oxygen for oxidative phosphorylation. We're going to see that these complexes have names that are pretty rational. NADHQ oxidoreductase, because it's moving electrons from NADH to Q. If we want simple names, this is complex 1. Electrons can be fed in at the level of Q by complex 2, succinate Q reductase. If we're looking at the main chain here, the Q is feeding into Q cytochrome C oxidoreductase, again, electron transfer, in the simple terminology, complex 3. And then the final complex in the chain, which is called complex 4, because this is the complex 2, the cytochrome C oxidase. So maybe this is a good time to take a break, and we'll distribute these from both sides. Here we go. All I ask you to do is to print your name and sign your name. And if you have suggestions for making the course better, feel free to put those on the back. Yeah, sure. Great. Yeah, you can pass those on down to the middle. Go. There you go. Hi. We will be offering these cards again at several more times during the semester, but I did think today being the last day before we go off on spring break. It's what? Yeah, all you need to do is print and sign your name. If you have suggestions, you're welcome to include them, but you don't have to do that. It's up to you. So I'll let you proceed with that, and we'll pick up again on the mitochondria. This is another representation of the mitochondria. This is the kind of classical shape that we just saw in the earlier slide. This can bring home to you what the mitochondria are like in an actual living cell. This central area is a nucleus, and the green here is a network of mitochondria that are serving it. The features are going to be common, whatever the shape of the mitochondria. Here again, very odd shapes of mitochondria in this particular cell. Whatever the shapes, they all have in common those features: an outer membrane, an inner membrane, an intermembrane space between those two, and a matrix that's inside of the whole thing. There's some reason to think that these different changes in shape between, say, that and that vary with metabolic demand and cell type. I think this one makes it a little easier to see that the crista here, this projection, is actually an extension of the inner membrane. So topologically, it's just part of the inner membrane. Okay. So I think I may not dwell in quite so much detail. I think I've been a little leisurely at this point. We were making up all that NADH from glycolysis out in the cytoplasm. And we need to get it to the electron transport chain in the mitochondria. And this is one of the kinds of strategies that can get used, which is to, we have, say, some, here we have the cytosol, they call it. It's the cytoplasm outside the mitochondrion. An aspartate can be transaminated to an oxaloacetate, and that oxaloacetate then can be reduced using the NADH as the reducing agent to a malate. The malate can be taken up in the mitochondrion. It can be used to regenerate that NADH, and so that malate is itself oxidized to oxaloacetate, and a transamination reaction in the mitochondrion can restore an aspartate that can then come across and do this again. So this is one of the ways in which the reducing equivalents can cross the mitochondrial membrane. And the enzymes here and here are different enzymes. We'll see this in a lot of places, that the same function may need to be done in more than one place, and in that case, there's usually isozymes for them. Another problem in thinking about oxidative phosphorylation is where stuff is made and used. We're going to see that, well, we know that most of the ATP is used in the cytoplasm. Most of the ATP is made in the mitochondrion. And so there's a problem there. And in making ATP, we need ADP as one of the substrates. And so it's not perhaps too surprising to see that there are transporters to work with this problem. And one of them will exchange ATP and ADP. And to the extent that there's a gradient, it'll just simply, tend to abolish that gradient. And then there's a second carrier. Since the ADP in here will also need a phosphate to become an ATP, there's another carrier, a phosphate carrier that's a co-transport of phosphate with protons. And so the fact that there's a proton gradient gives the mitochondrion a way to pull in the phosphate it needs to make ATP. So now we're actually looking at the first bit of the electron transport chain. This is complex 1, or NADHQ oxidoreductase, if you want the longer name. And it's astounding to me that we actually know what it looks like. This is the structure of the whole complex. It's quite a big thing with more than one piece to it. And it's embedded in a membrane to provide the sealant, if you like, between the two compartments. The complex 1 has a number of sites for electron transfers inside of it, so it's not just straight from an NADH straight to Q, do not pass go, do not collect $200. Those electrons pause at a number of places along the way. And this is showing you a few of the kinds of centers for those electrons along the way. There are iron-sulfur centers. This strategy of using iron and sulfur for redox reactions is played out a number of places. Some interesting evolutionary aspects about that if people want to talk about that. It uses one of the flavin compounds. In this case, it's flavin mononucleotide. And here's the flavin ring. And you can see here these double bonds, if you like, are being reduced to the single bond there. You can see the new hydrogens picked up and the electrons that have come in. Here's a smaller iron-sulfur center. And this is showing you that complex 1 in the context of the membrane. So complex 1, this is much less dramatic representation of it, is going to accomplish a number of things. It's going to transfer electrons from NADH through a series of transfers to Q to generate QH2. So there's 2 electrons coming from NADH to Q. That reaction will release an NAD+. Protons will be moved as a consequence of that redox reaction through the complex so that there's more protons now in the intermembrane space than there were before. We're starting to build up a proton gradient, an excess of protons in the intermembrane space. And this the redox reactions here are coupled to the movement of the protons. There's some thought that there may be, in effect, a proton wire, parts of the compound that are lined up to let the protons move along them. But they aren't necessarily the same protons that are coming off of the NADH. So that's complex 1. There's another source for electrons for ubiquinone. We mentioned this already, succinate dehydrogenase. Succinate dehydrogenase is one of the steps in the citric acid cycle. It is also an integral membrane protein. And in the reaction from succinate to fumarate, the electrons that are removed in that process are transferred to Q to generate more reduced Q. So this is one of the places where electrons can come in addition to complex 1. There are also some electrons that can come in through a glycerol phosphate shuttle. This is a way to move in electrons if aspartate is not particularly abundant. But the net result of it is, again, electrons transferred to Q. You'll notice that these 2 sources do not move protons. They just feed electrons into Q. So that's a difference between them and complex 1. So complex 3, which is the second in the sort of straight line, if you like, of the electron transport chain, is going to move electrons from ubiquinol to cytochrome B and C and ultimately to cytochrome C. This is an example of heme B. And you can see here an iron in an Fe3+ state in contrast to hemoglobin and myoglobin, where it's Fe+2. And the iron in there is capable of undergoing redox reactions. This is a sort of a more detailed look at what complex 3 looks like. You can see that some of these proteins, like the cytochromes, cytochrome B and C1, are actually integral membrane proteins. Their heme groups are aligned in ways that facilitate the movement of electrons. And part of what makes things complicated is that ubiquinone and ubiquinol involve 2 electrons altogether, whereas the cytochrome B can only transfer 1 electron at a time. And so the actual oxidation reduction takes place as a series of transfers called the Q cycle. I'm looking at the time, and I'm thinking So we have a reduced ubiquinol here with its 2 electrons and 2 hydrogens, which can donate those 2 electrons and come off as a plain old Q. Those 2 electrons are going to go to a couple of different places. One will be transferred to an iron sulfur center, to cytochrome C1, and ultimately to cytochrome C. And you can see out here that cytochrome C is outside the complex. It's actually a peripheral membrane protein, a protein that can almost roll along the surface, surface of the inner mitochondrial membrane. The other of the electrons from that ubiquinol is transferred to cytochrome B, and that empty Q that we released there can pick up the 1 electron. And in the second cycle, a fresh ubiquinol coming in gives off 2 electrons, and that half reduced one can pick up its second electron on the second stage in that cycle. And you'll notice that in this process, protons are again being moved into the intermembrane space. So the electrons from the ubiquinol are moving through complex 3. The protons are being pushed out into the intermembrane space. And this just shows you the net of that for every 2 molecules of ubiquinol, reduced ubiquinone, you can move electrons and generate molecules of cytochrome C. This is a ribbon diagram of cytochrome C, one of the early proteins to be characterized for its structure. And its job then is to carry these electrons from complex 3 to complex 4. Its peripheral membrane protein, ubiquinone, was in the membrane itself because it was a lipid-soluble compound. Cytochrome C is a protein. It's pretty much water-soluble. But you notice all these charged groups on it mean that it can kind of roll along the surface of the membrane. It doesn't get very far from it at rest. It can be pulled off the membrane with salt and stuff, but it spends a lot of its time on the surface of the membrane. Cytochrome C is a very conserved protein, so you can get cytochrome Cs from basically any eukaryote that will be recognizably cytochrome C. So we're moving these electrons, and here we are at the end of the chain. The last in the electron transfer chain is complex 4. We need to oxidize cytochrome C so it can go back and pick up more electrons. And the electrons that are going to come from cytochrome C will be transferred to oxygen and are going to reduce oxygen to H2O. Now, to turn O2 into H2O is going to take 4 electrons to make that happen. So we're going to need 4 cytochrome Cs per each O2 molecule. Within this large and ungainly complex, the electrons get transferred to a number of places again, the way they did in complex 1. There's copper elements. Heme A is buried in there. There are iron-copper groups and so on. So it's, again, not just a 1-2 kind of chain. There's lots of places within that complex that the electrons are going to move first. This behavior is stranger than you realize. I have made it sound very matter-of-fact and easy, which is misleading. Oxygen is corrosive. It's a nasty, nasty molecule. And partially oxidized or partially reduced oxygen is even worse. So there's got to be a trick here for how the complex 4 can manage its electrons. And the electrons that are coming in are always attached to particular carriers, to park it, so to speak, if you like, inside the complex 4. And this is sort of a schematic of that, of having iron and copper available in the center. An oxygen will come in and park on that Fe+2. We start to feed electrons into this special center for it. Now we have an iron that has lost electrons. It's at 4+ and has donated some to this oxygen, and a copper that has a hydroxyl group parked next to it. By passing one proton through there, we can pull that one off as a water. And then we have this oxygen 2- parked still on the iron. Some more electrons coming in. And we can see in this case the iron has been, in this case, reduced from 4+ to 3+. And the oxygen has received let me see. It's ready to pick up a proton and come off as water, and additional electrons are needed to reduce this further. So this has been restored to the initial starting state. So you're starting up here with iron and copper and get back to where you were. At no time are those oxygen atoms just free to go around and hit other stuff as well. What's also involved with these oxidations and reductions is there are protons that are moving out of the matrix into the intermembrane space. This is sort of another diagram of that kind of thing. Your cytochrome Cs are, it's a little bit darker than I meant it to be. Cytochrome Cs are peripheral membrane proteins acting in here to donate the electrons. Complex 4 does the final reduction of water, or transfers those electrons to water, to oxygen rather, in the matrix side. And in using up protons here to make water, it's reducing the concentration of protons in the matrix, which is increasing the gradient between the matrix and the intermembrane space. In addition to those protons, other protons are actually moved into the intermembrane space, so that altogether it builds up the proton gradient in several different ways. Well, how much good do these different things do? We can look at the potential drops at each of these complexes and translate that into free energy changes. And the free energy change associated with complex 1 is minus 70 kilojoules per mole, minus 37, minus 112. All three of these electron transfer complexes have more than enough energy to justify making an ATP. That is, they have a free energy change associated with them big enough to account for an ATP. We haven't seen any ATP anywhere in here yet, though. All we've seen is electrons moving and protons moving. This is just showing you that the various complexes of the mitochondrion are not just bouncing around, but in fact can be isolated as complexes, so that you can imagine electrons moving directly from complex 1 to 3 to 4 like that. These are not free scattered things floating around, but are probably associated in the mitochondria as well. So this gets us to chemiosmosis. This is the basis for actually generating some ATP that we can use later on. All the complexes we've looked at so far have had the net effect of moving protons into that intermembrane space. And we call this a chemiosmotic gradient. It's a chemical gradient because it's a concentration of protons. It's an electrical gradient because there's actually a charge difference across it. And that's not necessarily what would happen if there were carriers that allowed other positively charged things to come in. You could have a proton gradient with no charge gradient. In fact, the way mitochondria work, there's both an electrical and a chemical charge, a difference across it. For 2 electrons that move all the way from complex 1 through 4 and producing water, about 10 protons get moved. And it was Peter Mitchell who had the insight that it's the proton gradient that's going to be the mechanism that's used to generate ATP. It's also behind photosynthesis, so we'll be able to take a look at it in some detail then as well. I don't have time, I guess, to tell you great stories about Peter Mitchell, but if people want to hear it afterwards, stop by. He was an eccentric genius who used his personal fortune to do this. And for years, people were just going, oh, Peter Mitchell, he's crazy. But he was right. Sometimes the crazies are right. At any rate, so we've got a proton gradient. How do you turn a proton gradient into ATP? It's a very, very special protein complex called ATP synthase. And a longer name for it is F1, F0 ATP synthase. And what it's going to do is somehow or other use that proton gradient to flow downhill and in the process couple that movement of protons to making ATP from ADP, an inorganic phosphate. And the bottom component, the integral membrane component, is called F0, and it has special channels for the protons to move through. F1 is the peripheral component of it, and it's going to be the part that has the enzymatic activity that can make ATP for it. And the two of them are very closely coordinated in living cells. This general structure is deeply conserved. You can see things that look like this in E. coli as well as in us. This is a pretty much unique solution that's been reused many times. The F1, F0 ATPase is so big you can actually see it in electron micrographs. And by dint of great efforts, its actual structure has been analyzed, and here we've represented that structure using some colors to help keep track of which parts of it. So the F0 part of it is composed of proteins that are given Roman names like A and C units. And they are embedded in, here's the B unit that extends up from the membrane up. And then the F1 component that is more peripheral has all these Greek names for it. The F0 part always has at least an A and two B's to make the spike, and then 9 or more of the C subunits. The F1 component has a trimer here of alpha-beta dimers. So it has 3 A's and 3 B's alternating like that. It has this spindle structure of the gamma and epsilon and a delta protein spanning across. The integral membrane part, the F0 part, has this C ring and an A stationary part. The C ring actually rotates, and the protons enter from the intermembrane space, sort of channeled through the A subunit of it, can bind to carboxylates on the C unit. It'll have to rotate around to the next place of it on the A before the proton can escape to the other side. And because there's a gradient, it tends to go in that direction. If the gradient were in the opposite direction, it would rotate in the opposite direction. So it's the gradient that makes it go in one particular direction. The peripheral part, the sort of the bouquet of flowers sticking off of that, is itself stationary. So this is now the F1 part that is peripheral to that ring, and the alpha-beta trimer does not move. The A subunit in the membrane is fixed. The alpha-beta trimer is fixed. And it stays fixed because of the, if we go back a page, sorry. You remember here the B and the delta subunits help anchor the alpha-beta trimer from moving. So they are going to help contribute to it staying still. In the center, you have the other components. You have the gamma, and the gamma is going to turn as the C ring turns. So the gamma is going to communicate that movement up into the alpha-beta trimer. And when the gamma turns, as it touches the dimers, it changes their conformation. So now we're looking down on the top of the ATP synthase. We're looking at the flower bouquet that's got the trimer. And what we can see is that each of the subunits, each of the dimers, has any of 3 states it could exist in. And which of them it's in will depend on how that gamma thing is touching it. And here they've given it kind of schematically an asymmetric shape, so that's easier to see. There's an open configuration in which ADP and PI can enter. When that central rotor rotates, you can see it here in the bound state, in the loose state. With one more rotation, that top one now is in a tight state with ATP in it, and when it comes back around to the open state, that ATP comes out. And each of the sites on that trimer goes through that same cycle every time. I think we're going to skip dinitrophenol. I do want to mention this idea that electron transport is coupled to making ATP. If you don't have a proton gradient, you don't get ATP. So you can have electrons moving, but if the membrane is broken in some way so the protons leak back, you can be doing lots of electron transfer and no ATP production. And when things that can do that are called uncouplers. They uncouple electron movement from ATP synthesis. Okay. I will leave the amazing hibernating bear for your entertainment. Have a great day, great spring break. Make sure you leave your cards at the front, okay? Make sure you leave your cards at the front.